the elimination of unplanned downtime, we have converted to additional output. So those are the most significant measurements. We've also noticed that in those departments, within a few weeks after going through the process, that we tend to have a reduction in our unit cost in those departments as well. I think a lot of that's due to the fact that with the same number of people, we are getting more product out of those areas.
The results of TPM in our plant have been really phenomenal. I mean, if you look at our cost per barrel has improved significantly from the time we've started up. And right now, I'd say there's no end in sight because there's still so many things that we can still do better, that we can improve on.
The major thrust is basically to be able to build more good parts in a given period of time. Whenever a machine doesn't do its job properly, it makes the cost of that part go up. And one of our big thrusts right now in the company is to try and take some of the cost out of building airplanes.
Hello, and welcome once again to Teletrain's series on total productive maintenance. For Teletrain, I'm Bill Quiet. In this program, we'll continue our examination of preventive maintenance. There are 4 types of preventive maintenance techniques which provide our focus. The first 2, daily routines and scheduled outages, are addressed in a separate program. In this program, we'll explore predictive maintenance and condition-based maintenance. Condition-based maintenance employs many or perhaps all of the techniques of predictive maintenance. The primary difference between the two is that condition-based maintenance provides continuous monitoring of equipment, whereas predictive maintenance is based on scheduled inspections or routes. The goal of both disciplines, however, is fundamentally the same. They are used to evaluate the wear of critical components in hopes of anticipating or predicting equipment failure. To understand the importance of the function they serve, we'll quickly review the thinking behind scheduled outages. A scheduled outage involves the planned shutdown and thorough inspection of critical pieces of equipment. Parts which are found to be badly worn and nearing the end of their life cycle are replaced, even though they haven't yet failed. This practice is known as proactive replacement, and it can be an expensive proposition, but if managed properly, it's less expensive than the lost production caused by equipment failures. In the case of highly complex equipment or extremely large, heavy equipment, such as shown here, the cost of lost production is compounded by the time required to break down the equipment and get to hard-to-reach components. In this case, small and relatively inexpensive roller elements are being replaced. You can easily see that it's much cheaper and less time-consuming to replace them all at once than it would be to shut the equipment down several times and replace them individually. The challenge is in knowing how often or at what intervals to conduct proactive replacement.
I've heard it said by many that there can be substantial upfront costs going from a traditional reactive maintenance program to a long-term proactive maintenance program, but quite frankly, that has not been our experience. There is so much waste in the work processes that we utilize today, and I don't mean just Dow or the chemical industry or even North American industry. In any work process, there's lots of waste. And if you can identify those elements of that waste early on in the process and pick the low-hanging fruit, I'm convinced you can pay for any what might be otherwise upfront costs associated with this transition and maintain a stable cost picture until you're able to make these tremendous, and I mean tremendous, 30, 40, 50% cost reductions in what it costs to maintain assets over the longer haul.
You know, the cost of getting it done is not an issue with me, as it was early on in my introduction to the concept, because in my mind I thought, okay, we got to go out here and remodify this drawing machine, we got to modify this spinning machine. And you know, the fact of the matter of the whole situation was that I did not realize that just a little bit of maintaining, a little bit of cleaning, you know, yielded so many opportunities that it did not cost us a lot of money to do that, you know. And so as I talk about cost, it's not an issue with me. It's not an issue with me.
If we could chart the life cycle of a particular part, we could watch the level of deterioration increase over time until eventually the part failed. If we were to replace the part at this point in time, based on our schedule of planned outages, we would be replacing it unnecessarily early and wasting money. If, however, we plan to wait until this point in time, we've waited too long, and an even more expensive breakdown would already have occurred. The ideal time to replace the part would be somewhere in this area. We would be utilizing a very high percentage of the life of the part, but replacing it prior to failure. The trick is knowing when we've reached this point. Well, maybe time isn't the best way to estimate relative wear. Suppose we could set some type of a control limit at approximately this level of deterioration. When the control limit is reached, we replace the part. This type of thinking has been used in automobiles for some time. Brake pads are equipped with soft metal pins recessed into the pad. When the pad is worn thin, the pins come in contact with the brake rotor and create a loud squeal, which tells the operator it's time for replacement. Predictive maintenance works in the same way. A physical characteristic or parameter is identified and measured against an engineering limit. When the limit is reached, it's time for replacement. The physical characteristics which might indicate excessive wear or deterioration of equipment include heat and vibration, and some which are not readily detected by human senses. Notice in our example of the automobile, the extent of brake pad wear is not easily inspected. That's why another form of inspection was devised. Predictive maintenance techniques often work in the same way. They enhance your ability to evaluate physical conditions which may not be immediately apparent. To illustrate this point, we'll show you a training device used by the Boeing company to introduce predictive maintenance techniques. The drum on the end of the motor shaft is there simply to create a load, which the motor must turn. To the naked eye, the motor works perfectly well when switched on. But when a strobe light is shined on the motor windings, the presence of a problem is unmistakable. Internal wear has led to a wobble in the shaft, which will eventually destroy the motor and may destroy a coupling or even the driven unit in the process. Now that we've introduced some of the thinking involved in predictive maintenance, we'll show you some of the most widely used techniques. We'll start with some rather simple ones and try to show you how the practice has become more sophisticated in recent years. We all know that a great deal of metal is used in modern equipment and facilities, but as metal ages, it can weaken. How could we evaluate its level of deterioration? If an exterior crack is present, that certainly makes the job easier, but hairline cracks can be very hard to detect, and if they're filled with dirt, almost impossible. But once the dirt has been washed away, a liquid penetrant or dye may be applied. The dye will tend to seep into the crack through what is known as capillary action. When excess dye is wiped away and a developer is applied, the dye and the crack become highly visible. But what if the defect is internal and no exterior crack is present? In this case, a probe containing a transmitter receiver is used to send ultrasonic waves through the metal. The defect will cause the waves to echo back to the probe, indicating its presence. This technology is used by Alumax to test the aluminum it manufactures. These rods are made by literally pouring molten aluminum through an orifice at a controlled rate and then quickly cooling it. When the pour is first initiated, the formation of solid aluminum requires a second or two to stabilize. So it is not uncommon to find tiny defects in the very bottom of the rods which are formed first. These defects are detectable with ultrasonic testing. The inspector applies a drop of oil to the surface to get a good contact with the probe. The handheld unit, which receives information from the probe, will indicate the presence of a defect if in fact there is one. If one is found, it is marked and this piece of the rod is removed. Another predictive maintenance technique involves oil analysis. A sample of oil is drawn and then sent to a lab where it is analyzed microscopically to determine the amount of particle content and the size of the particles. This test will tell you if the oil needs to be filtered or changed, and will also tell you something about the effectiveness of your oil filtration system. If particulate content is high, a process known as spectrographic analysis may be performed to identify the types of metal found in the particles. This will tell which metal surfaces in the system are deteriorating. But at this point, deterioration is already well underway. Newer devices can be used at the equipment rather than in the lab to evaluate the oil itself rather than the particle content. This device measures the viscosity of the oil and its capacity to provide adequate lubrication. When the oil begins to deteriorate, it is changed before the equipment begins to deteriorate. An important consideration in oil analysis is deciding where to draw your sample. Should it be upstream or downstream from the filter? That depends in large part on what you're testing for. Now let's move on to even more advanced forms of predictive maintenance. Vibration analysis is probably the most widely used predictive technique, but new applications are being found for it every day. We'll start by explaining how it works. All equipment vibrates when it is energized and working, even if it is performing perfectly. With equipment age or deterioration, the vibration becomes more pronounced. The vibration is actually a continuous series of tiny back and forth movements, which we can illustrate as a waveform. And we can evaluate the wave 4 separate ways. Frequency is the number of back and forth movements completed in 1 second. Displacement is the total distance traveled in one movement. Velocity is the speed at which the movement is made. And acceleration is the rate at which the speed rises and falls as each tiny movement is completed and a new one begins. Any one of these parameters can be used to measure vibration, although the last 3 are the most common. Some care should be taken when selecting vibration analysis equipment to ensure that the parameter being measured is the most appropriate for the type of equipment being evaluated. Most analysis equipment consists of a probe and an electronic recorder. The recorder is loaded with a route or list of equipment which the technician is to evaluate. Readings are taken at predetermined points on the equipment, and the recorder stores the data until it is returned to the computer which loaded the route and evaluates the data. Over a period of time, the computer builds a database of the vibration patterns demonstrated by each piece of equipment or component parts. Once a sufficient database has been collected, it is possible to evaluate the equipment's need for maintenance and to estimate the life expectancy of the components. If enough energy and resources are dedicated to vibration analysis, it is possible to evaluate equipment in remarkable detail. Not only can the impending failure of, say, a bearing be detected, the problem can be isolated to the inner and outer races. But this requires the ability to handle an extraordinary amount of data. Some organizations have tried to simplify the process by looking primarily at trends or by purchasing less expensive equipment to spot check for spikes. The last predictive maintenance technique we will address is thermography, or the study of heat patterns. In this photograph, we see a 400 amp fuse located in a motor control center. The system is operating normally, and there is no reason to suspect a growing problem until we see the fuse under infrared photography. A temperature rise of 9 degrees Celsius is found, and the pattern of the heat suggests that a poor connection exists between the fuse and the load side fuse clip. In this infrared shot, the heat pattern is concentrated in the line side of the fuse, even though this is only a 200 amp fuse as compared to the 400 amp fuse we just saw. The temperature increase is 33% greater. This is a fuse about to fail. In this shot, we see evidence of oxidation in the wire running from the load side of the fuse to the line side of a motor starter. This shot is especially interesting. Again, we see evidence of excessive heat, and this time the temperature rise is severe, 35 degrees Celsius. But the pattern of the heat is most revealing. The 2 outside fuses show hot, but the middle one does not. This suggests a possible phase imbalance. Now, let's look at some larger equipment, such as this transformer. A failure here might interrupt power to a great deal of equipment. Under infrared, we find evidence of a bad connection. Again, we are looking at major electrical supply equipment. And again, we see evidence of a bad connection. Infrared photography not only provides another way to look at equipment and forecast problems, some insurance providers have come to recognize the value it has in terms of safety and fire prevention. Infrared video is now finding use in addition to infrared stills. It has several advantages. For one thing, it allows equipment to be monitored in continuous process rather than just in freeze frames. It doesn't require time for film development. Some infrared video cameras can go in and out of normal vision, which makes it easier to orient the picture to the area and identify equipment. And it's easier to zoom in on hotspots to pinpoint problem areas. We'll end this program with just a few words on condition-based maintenance. It differs from predictive maintenance only in that the sensing devices are permanently mounted on the equipment rather than carried to equipment by employees. This makes testing in hazardous environments a more viable possibility. And it's also a great help in modern facilities where the job of operator has greatly changed. The work is performed in front of a computer screen rather in front of a piece of equipment. By providing real-time monitoring of remote equipment in a central location, condition-based maintenance offers a great deal of flexibility and many options. Equipment conditions can be automatically monitored and alarms established based on set points, or the monitors can be wired directly into control devices for automatic adjustments, or into a computerized maintenance management system for data analysis. Clearly, this is principally the domain of highly automated processes. You're probably familiar with the term root cause of a failure. It suggests that one problem led to another until the problems became so severe that a breakdown occurred. In some ways, troubleshooting is a process of looking back in time to find that original problem. Predictive maintenance, on the other hand, attempts to look forward in time and brings us one step closer to fixing problems before they happen. Thank you for joining us. For Teletrain, I'm Bill Quiet.